Hello everyone, welcome to the second talk here. Jay Moondra is a fourth-year PhD student at the School of Computer Science at Georgia Tech. He was advised by Swati Gupta from MIT and Mohler Singh from Georgia Tech. He finished his BTech in CSC from Delhi in 2019. His research broadly focuses on discrete optimization and applications to algorithmic fairness, quantum computing, and machine learning. And we are very pleased to have him here. And
Thank you so much for inviting me. And I will talk about the NISQ problem and the quantum approximate optimization algorithm. I will start this talk by saying that I'm not a physicist, so any mistakes in physics, I should be excused. And I approach this thing mostly from a discrete optimization point of view, but of course I'll go into some of the quantum computing parts, and I'll try in the first third of the talk or so to give the idea of what QAOA is. All of that work is all before me and my collaborators. And then in the second and third half of the talk, third of the talk, I'll try to go into our contributions and how we enhance QAOA and so on. Right? And this is joint work with a lot of my fantastic collaborators: Bryan Gard, Swati Gupta, Creston Herold, Philip Lotshaw, Greg Mohler, Joel Rajakumar, and Reuben Tate. This is a result of 3 papers. So very briefly about me. So I do approximation algorithms and some machine learning and then things at the intersection. But somehow I got involved in quantum computing. And in quantum computing, I'm going to speak about hybrid quantum and classical algorithms, specifically for max-cut, and some quantum noise reduction, which is a big issue with quantum computers. Right. So this is the outline of the talk. So I'm going to introduce the algorithm QAOA for max-cut. Then I'm going to talk about warm starts in QAOA. I'm going to talk about what are known as custom mixers, and then some empirical results there. In the second half of the talk, I'm going to talk about how do you even implement these algorithms. In theory, it's possible to, but in practice, there are issues such as noise, and then there are also issues of how to even construct quantum gates. So that will be the second half of the talk, which will also feature some devices from classical computing. Right. So let me get started. So what is QAOA? So it was introduced by Farhi et al. In 2014. So it's a hybrid classical quantum algorithm for max-cut and other problems. It was introduced for max-cut, but it can be applied to many other problems like in a max independent set and so on. So it's a somewhat promising candidate for these problems. It achieves approximation ratio greater than or equal to 0.755 for 3 regular graphs, as they showed in their original paper. Now, of course, this is worse than what we know for 3 regular graphs in classical computing. Nevertheless, it's still non-trivial, and this is not known to be tight. This is from a very simple analysis, so we don't know if we can improve this or how much we can improve this. Unknown if it beats classical bounds in a polynomial number of operations.
What does it mean to be a hybrid classical quantum algorithm?
It could mean various things, but one of the things it could mean is that you run the quantum computer for a bit, and then you use a classical computer based on the output of the quantum computer, and then you feed whatever output the classical computer gave back into the quantum computer and so on. So you kind of constantly switch between the two at a very rough level.
But then why do I need to switch? Why can't I just use a quantum computer? Why isn't any quantum algorithm like this? Decoherence.
Yes, that's one of the reasons. In the short term, there is a lot of noise and you want to reduce the noise. But also there's evidence that using such hybrid approaches could beat any pure approaches of just using classical computing or just using quantum computing. I'll present some empirical evidence and a little bit of theoretical evidence there, which in theory should not be very surprising because you're using the best of both worlds in some sense. So that's
what are the advantages that classical computing have over computing?
It is, I believe there are a few problems where we know that classical computing is faster than quantum computing.
But that is, I mean, like reversible, like it's very small order.
Yeah.
Yes, yeah,
That's just like when whatever you get out of reversibility.
right, yes. So there is,
But I think in this case, the issue is that the quantum part here is of a very special kind, because adiabatic, the changing one Hamiltonian slowly.
right,
It's not general quantum computing.
it is not,
Like, because general quantum computing, at least from probabilistic theoretic point of view, should be at least as good as P. I mean, like BQP should, anything in BQP is also in P. I mean, like, more or in BQP by definition.
I believe, so, yeah.
So,
Everything is also.
anything in BQP. Sorry, the other way around. Anything
Sorry, yeah.
in BQP, yeah.
So-
So, if you have an algorithm that is a quantum algorithm, if you have a classical algorithm, it's also a quantum algorithm. Because it's just diagonal things.
Right. So in the context of max cut, the advantage classical computers have is that we already have very good algorithms in classical world, which we don't know what the direct analog is in the quantum world.
I mean, it's the same circuit you could take and put it on the quantum, general quantum.
You could.
The
There are
issue with QAOA is that it's not a general.
QAOA itself is not a general.
Yeah.
That is true.
So that is supposed to be that one. Like it's quite easier to implement than general purpose quantum.
Sure. Yeah. Even though there are issues even with the implementation of QAOA that I right. So it's unknown if it beats the classical bounds, although it is widely conjectured that it does. A lot of people believe that. In what is called the adiabatic limit, as in if you keep running it for a very large number of gates, the approximation ratio approaches 1 if you run QAOA, and I'll make precise what that means. But it's not known if that sort of limit can be achieved. Like you can get close enough to 1 in a polynomial number of operations. We don't know if you can get to 1 minus epsilon in a polynomial number of quantum gates, right? So it is, and then QAOA itself is motivated by what's called adiabatic quantum computing. And I'll once again try to make precise what this is. But let me get started with some really basic setup of quantum computing. And my aim here is to.
So adiabatic quantum computing is not universal. It is.
No, I think in
No, but
general form it is.
Huh?
General form it is, like you can. Okay, I don't know I mean, it depends upon how this schedule, right? I mean, so like, I mean, any problem and you could write down a Hamiltonian for it and try to approach it in that limit that it's saying. But whether it is known that anything that is polynomial time doable is also like a schedule that is important, I don't know. It probably is known, but I don't know.
In terms of the Turing computability or whatever the equivalent is in the quantum world, the approaches of quantum circuits and adiabatic computing, they're like same. So any problem that you could solve with one approach, you could with other.
But the loss. Yeah.
Yes. So
is it polynomial?
So I don't know that actually. Yeah. So that I'm not sure. Yeah. So let me just try to say what the mathematics of this is and try to abstract out the physics for a bit, right? And so for me, one qubit quantum state is just a vector on this unit sphere in 2 dimensions. This is the complex unit sphere, and that's what 1 qubit is, right? And so let me look at the standard coordinate axes. The first one I'm going to call the 0 bit, and the second one I'm going to call the 1 bit. This is slightly unfortunate notation because zeros and ones are being used in 2 different sense here. But basically think of one axis as the 0 bit and the other axis as the 1 bit. And because you have something on the unit sphere, I can of course write it as a combination of these, right? A linear combination of these. So that's my quantum state. And this is a superposition state. Unlike classical bit, you can be a little bit in the 0 bit and a little bit in the 1 bit. And when psi is observed, when you try to observe psi, it collapses to either 0 or 1. It collapses to the 0 bit with probability that's given by psi naught squared, the coefficient squared, or the absolute value squared, and to the 1 bit with the corresponding coefficient squared, right? And of course, those add up to 1. And what is a quantum gate? A quantum gate for me is just a unitary matrix, a rotation matrix. So it's a 2 × 2 unitary matrix, and a quantum circuit is just a sequence of these matrices. So that's it for me. So I'll start with in a state psi naught. And then I'll keep applying some of these gates, which is my quantum circuit, and I'll go to psi L.
Why do you need, isn't the product of unitary matrix also unitary?
It is, yeah.
So why do you need many of them?
So you also need to construct these matrices. In theory, you could just have one, but it's like in the classical computing thing, you compose these AND and NOT gates to create a bigger circuit. And so
But fanning is restricted. So each unitary operator is on a constant number of qubits.
No, it's still the same number.
No, that is it's like 2 tensor. So each of those things in principle. So these things could be larger, more qubits, and each.
Which things?
So
I don't know what you're pointing.
No, so this psi 0 need not be 1 qubit, right? In the general case, there will be many qubits, and but the unitaries you will use will be 1 or 2 qubits. That's what you want, 1, 2, or 3. It's just like classical. You want gates which are bounded, and you want to have a finite number of them. Usually. Like you want to only make some small fixed number of gates, and everything has to be composed from them.
Okay.
and I'll get to the general qubit systems quickly. So, but before I do that, this is a nice visualization of what a 1 qubit system looks like. Now, of course, if this was all in the real field, then I could just draw a circle with the x-axis representing the 0 bit and the y-axis representing the 1 bit. But because we are in the complex field, let me introduce this tool, which is not quite a generalization of the circle I mentioned. It is slightly different in that the first coordinate axis or the 0 bit is on the top there, and the 1 is at the bottom here. What I'll do is I'll take a quantum state psi and I'll write it as something times the 0 bit plus something times the 1 bit. That first something, let me abstract out the phase, as in, let me assume it's a real number and not a complex number. And in fact, a real number between 0 and 1. So a non-negative real number. So I've abstracted out the phase element of it, but it's still nevertheless a very useful visualization tool, and more than that actually, so I'll get to that. So let me write this quantum state like this, or any quantum states that can be written like this. I'll represent it on this sphere where my psi will be given, like that is how I'll get the coordinates, right? It will make an angle theta with the z-axis, and in the xy plane, the angle with the x-axis is going to be phi. We will get back to this sort of visualization later on. Some fundamental gates in a 1 qubit system are the poly gates. The poly X gate basically flips the qubits, maps 0 to 1 and 1 to 0. The Y gate basically maps 0 to minus I times 1 and 1 to I times 0. The Z gate, and this is going to be the most crucial one for MaxCut, it maps the 0 bit to 0, but it maps the 1 bit to its negation. And this is how we are going to, this is going to be the most crucial ingredient for MaxCut problem. And I'll remind everyone of what this is later on. So now let me generalize everything to a 2 qubit system and then to an n qubit system. So now I have a vector in 4-dimensional unit sphere, so that's 2 to the 2. And those 4 coordinate axes with the standard basis, I'm going to call the 0, 0, 0, 1, 1, 0, 1, 1 states. And any quantum state in 2 dimension can be written as a linear combination of these, right? And as an optimizer or as a computer scientist, I'm going to think of these as bit strings. So I have 4 bit strings, and I'm in a linear combination of these 4 bit strings. We'll deal with what are known as separable states and non-separable states. Very quickly, what are these? So let's forget about the weird-looking product there. That's the Kronecker product. It simply means that you can essentially factorize this state into the first qubit times the second qubit. And so your coefficients are nicely given by this, but you cannot always do this. So if you try to write this quantum state as something like that, you will not be able to factorize it. And we'll deal with both separable and non-separable states. So, right. And now for me, I'll restrict calling a quantum circuit just a bunch of unitary gates, right? So this is what a quantum circuit is for me, or at least the quantum circuits I'm going to deal with. And these are 4x4 matrices, right? Let me just quickly say what an n-qubit quantum system is. It is a vector in the 2 to the n dimensional space on the unit sphere. And what are so there are going to be 2 to the n standard coordinate axes, and I'm going to map each of them to some n length bit string. So there are going to be 2 to the n of them, and so I'll have a mapping between the coordinate axes and the classical quantum states, right? So nice. So we are in the superposition of these 2 to the n classical states. And once again, a quantum gate is going to be a 2 to the n dimensional unitary matrix, so a large unitary matrix. And this is going to be my quantum circuit. When I observe psi, it's going to collapse to one of the classical bit strings with probability given by the coefficient squared, right? For each of the classical bit strings. Now let me talk about max cut. So given an undirected graph, a weighted graph, so the weights are W, we assume they are non-negative, and a vertex set S that's subset of V. The cut value of S is the total weight of edges that cross from S to V minus S. And the max cut in G is you find the S that has the highest cut value. And a very simple example, so this is my graph, those are the edge weights, and so this is one max cut of value 4, that's where you cut. This is another max cut of value 4, there's another one in this graph, but our goal is to find a max cut in graphs. We'll also identify the subsets with the bit strings of length n. So if the bit string, so if a certain coordinate is 0, that means that vertex is on one side of the cut. If that coordinate is 1, it's on the other side, and this will be a useful way to look at it. It's an NP-hard problem. 0.878 approximation is known. In 1994, a better approximation does not exist, assuming the unique Games conjecture. And if you just assume that P is not equal to NP, then the bound is something like 0.94. But most people believe that this is the right bound. Right. And so now let me combine the two words, right? So now let me show how max cut is an eigenvalue problem. Right. So recall our poly gates, and now we are in 2 to the n dimensional space. So we are with n quantum bits. So let me construct a gate which I call sigma jz. So if I take a classical bit string, so that's the bold B there. So this sigma jz maps B to B if the jth bit is 0, and it maps it to minus B if the jth bit is 1, right? So, all right. So now what happens if I take two different vertices J and K, right? So two different bits. So what will happen if I take this product? Then I'll get, when operated on a classical bit string, I'll get B if the corresponding vertices are on the same side, they're both 1 or they're both 0, same side of the cut, and I'll get minus B if they are on the others on two different sides of the cut, right? And this is basically a construction of max cut, because now the cut value of a bit string can be written in this way. So what am I doing? I'm just taking that sort of expression, I'm manipulating it a little bit and multiplying it by the edge weight. So this thing here, it is going to evaluate to 0 if J and K are on the same side of the cut, and this thing is going to evaluate to 2 if they are on the opposite side of the cut by this expression, right? And so this expression on the left is going to be exactly the cut value of that bit string times B, which means that if I call this thing HC, this big matrix, then the eigenvectors of HC are the classical bit strings, and the eigenvalues are the cut values. So this is an eigenvalue problem, because finding the max cut now means finding the largest eigenvalue of this matrix. So we reduced max cut to an eigenvalue problem, although it's an eigenvalue problem in 2 to the n dimensions. Right. We call this HC a cost Hamiltonian. Equivalently, let me write it this way, right? Because we want unitary matrices. So let me write it this way. This becomes a unitary matrix. And once again, you preserve these eigenvalues in terms of the phase there. Right. So now let me talk about. Yeah.
There's like fractional max curve, right? I mean, what is kind of fractional value here?
So right now on this page, I just assume that these are just classical bit strings. Yeah. Yeah. So these are just classical states right now. Yeah, you could of course have a superposition of course. So want the highest eigenvector of HC. Suppose for some other HB, some other matrix HB, right? I knew the highest eigenvector. And what I'm going to do is, this is the idea of adiabatic quantum computing. I'm going to slowly evolve HB into HC. And I'm going to start my quantum state at the known highest eigenvector of HB. And hopefully as the quantum system evolves, and I'm going to specify what evolving means, hopefully as it evolves, this thing evolves to the highest eigenvector of HC. And that's sort of the rough idea. Of course, I'll have to specify what evolution means, and I'll have to specify how to convert that evolution into a quantum circuit. Yeah. So this is the setup. So given a Hermitian matrix H, let's look at this sort of Schrodinger equation, right? This is just a differential equation for me. And if I solve this, then I get this solution, which you can check. It's a solution by inspection. Right. In particular, if the original state psi naught was the unique highest eigenvector of H, right? Then psi t simply becomes a phase shift times the original highest eigenvector. And now suppose, so this is a very simple system. Now suppose you want to find the highest eigenvector of some HC. What I'll do is I'll define a time varying Hamiltonian. So HB is a matrix that I know the highest eigenvalue of. HC is a matrix that I want the highest eigenvalue of. And I have a time horizon capital T. And what I'm going to do is I'm going to vary my time small t from 0 to capital T, so that at small t equals 0, I have this matrix as equal to HB, a very nice world where we know the answers. And at time t equals capital T, this matrix becomes HC, a world where we want to know the answers in. Right, yeah, so that's the idea. And now I consider the time evolution similar to what I wrote previously, except that this H was a constant there. Now I'm just varying this H according to this equation, right? And so adiabatic theorem proven almost 100 years ago, and I'm stating it very informally here. So if at each time small t, it has a distinct highest eigenvector, meaning that the highest two eigenvalues are not the same, or the highest two eigenvalues by absolute value are not the same, then, and if you start with the highest eigenvector of HB at a time t equals 0, then as you increase this time t, right, then you will essentially recover the highest eigenvector of the cost Hamiltonian HC, which is what you want. Once again, this is just a physical system evolution. It's still not a quantum circuit. So now
what does it mean Hamiltonian? Is it Hermitian? What
it's just a Hermitian matrix. Yeah.
Why are you calling it Hamiltonian?
Why am I calling it Hamiltonian? I don't really know. The mathematical assumption is just that it's Hermitian. I think it just works out that way.
So the Hamiltonian in quantum mechanics turns out to be a Hermitian operator. That's Hamiltonian.
So what is the Hamiltonian?
Hamiltonian is the energy function essentially.
Oh, okay.
In general, in quantum mechanics, it turns out to be a Hermitian.
Whether it's one B and F, Max Born.
Yes, it is Max Born, and I don't know who F is, but yeah, I should know, but yeah, that is Max Born. So now let me try to discretize it, right? Like we optimizers really like to discretize continuous processes. So let me try to do discretization, and this is where the magic comes up. So once again, I have this time evolution, and so now let me try to write down this equation, right? Let me try to write down this equation. So on the left, let me write this down as a difference instead of a derivative. And that difference is just this divided by alpha. I just took alpha to the other side. So I get this very nice equation, and now it's more of a discrete process. Let's rewrite this, right? Let's rewrite this. I take the I to the other side, so that becomes minus I, and I take the psi t to the other side. So I get psi of t plus alpha is equal to I minus this times psi t. And once again, optimizers really like to write this in the exponential form. So I'll just write this as this exponential, because now this is very nice. This gives me something similar to a quantum circuit. I am trying to evolve this quantum state based on this quantum circuit. Right, to use quantum gates, let's approximate this as, let me just plug in this definition. So I get e to the minus I times something times hv times e to the minus I times something times hc times psi t. And these are two quantum gates. How am I approximating this? Of course, this is not inequality because these matrices may not commute, but this is called trotterization, where these numbers alpha times 1 minus 1 over t. If alpha is small enough, basically, this is an approximation. So this is just a motivation. This is not a formal proof. And once again, this approximation also holds when alpha is really small, right? So this is the key idea. And so what this is the QAOA description basically here. I'm just gonna get a sequence of these gates where I'm just gonna evolve psi t to psi t plus 1 by applying two of these gates, where beta and gamma are going to be chosen by maximizing this thing, which is exactly the sort of the quantity we want, the cut value of psi t plus 1. This is the cut value of psi t plus 1. And the discrete adiabatic theorem says basically it's an analog of the continuous one, that if you start again in the highest eigenvector of HB, and if you keep maintaining a unique highest eigenvalue, then eventually you are going to converge to the highest eigenvector of HC as your time horizon. This time it's a discrete time horizon as it goes to infinity. And capital T is just now the half the number of gates in your quantum circuit. Right, and so QAOA is this. So I have some HB, so let's not worry about it. It's just some nice matrix that satisfies this one property, that if I take the superposition of all states, so all bit strings taken uniformly, right? Then that becomes the highest eigenvector of HB. It's a uniform superposition of all bit strings. We call that a cost Hamiltonian. We are seeking its highest eigenvalue, just the max cut. And I'm just going to apply a bunch of these gates that look like this, which are motivated by adiabatic computing. The number of times I apply it, let me call it faulty, that's the circuit depth. And beta t and gamma t at each step are chosen to maximize. So once you have psi t minus 1, you'll choose beta t and gamma t to maximize this thing, which is going to be the cut value of this big vector psi t. And so that's QAOA, and that's already been done in 2014. The limitations are that it's promising for NPR problems, as I mentioned, but the limitations are that, okay, one of the results is there are deregular graphs where if your depth is, even if your depth is log n over d, right? So think of d as a constant, like 3 or 4 or something, then QAOA achieves at most 0.833, which is bad, right? Because Goemans-Williamson will do 0.878. And even with the logarithmic depth, you are achieving lesser than that. So that's one limitation. And many such results are made for different graph families and then constant depth or like logarithmic depth and so on. And so this is very like disappointing, because this might mean that QAOA does not work well. And so we might want to improve QAOA, have its variants that outperform these limitations and so on. And one of the ideas is the following, right? So it's not clear why we should start at the uniform superposition of all bit strings. That's what we start with. Let's start QAOA. We might already know something using classical algorithms, that this may be a more reasonable bit string with the higher cut value. So let's try to warm start QAOA to achieve faster convergence. And so now I'm going to let,
Just go back one second.
Yeah.
No.
oh, here,
Yeah, so when you say this, people proved, these are inferior to classical algorithms, it's with the assumption that the starting state was this uniform superposition.
yes,
If you start with an arbitrary state, then it's not clear.
then it's not clear, but then
You could start with the solution. We could start with the solution.
Oh, we start with.
but so suppose you start with a non-solution, then it's not clear if those variants even converge. So the theorem I just mentioned, right?
Oh, that's also popular.
That's also not a given. So maybe they do better, but what's the convergence guarantee there? And that I'm going to speak about that. Yeah. So because you need to, whatever your starting state be, in which case, in our case, it was uniform superposition, but whatever you have to find a matrix such that this vector is the unique highest eigenvector of this matrix. So you have to construct a corresponding matrix like this.
Sorry, can you just go back to the definition of the QAOA? Just here. No, what is happening? So earlier it just felt that you start with some matrix where you have some control, and there is this final matrix whose eigenvectors are going to whose bit string eigenvectors are going to tell you what the cut is, and the eigenvalue tells you what the size, the weighted size of the cut is. And now you want to somehow go from this thing that you have control over to there. And now the QAOA description is saying something about how you are achieving.
Right. Yeah.
But there's a flipping between HB, HC, HB, HC.
Yeah.
So what? Then just parse it. What is it saying? What are we doing?
So I don't have a good intuition except that this is a discretization of the adiabatic process that I just mentioned. So it simply is, I just write down this as an approximation. So I have just discretized the continuous adiabatic process, and that's the form it takes. I don't have a geometric intuition of.
One way that the e to the power a plus b is not the same as e to the power a times e to the power b. That is not true. But what is true is what doctorization means. That e to the power a plus b is, if n is large, then it is e to the power a by n times e to the power b by n. This whole thing raised to the power. So if you are going to alternate e to the power a by n, e to the power b by n, e to the power a by n, e to the power b by n, as n goes to infinity, this will go to e to the power a. So this is yes. So yeah, so the non-commutativity comes. So that is one reason why you have alternation you expect to have. And this n and t here are being similar. You are trying to discretize that curve. So slaughteration is a limit statement. As n goes to infinity, these things are okay. And so that is.
No, so, I mean, I'm assuming that this HC, that Hamiltonian, is very hard to prepare, right? Because if you could prepare that anyway, you solve the problem.
No, Hamiltonian might be easy to prepare, but you want to still get to its ground state. So you are not interested in the Hamiltonian, it's the ground state you will. Like the lowest energy state, or the
The eigenvalue,
the top eigenvector,
The top eigenvector.
lowest physics. So eigenvalue wise, so like this thing is just the easy model, the HC. So in that sense, it is maybe not so complicated to prepare the Hamiltonian itself or a system which has that, but you want to also get to the lowest energy.
No, but then why do you start from H, if HC is easy to prepare?
But the ground state of the other one is.
The ground state.
Yeah, so the other one was this, like what I think we call transverse field, right? It's sigma x. But now the ground state becomes as a uniform superfield. I mean, one question I had is why not start with summation sigmas? But I mean that is like it looks a bit strange because now the ground state will be the all zero, like which basically everyone is on one side, which is clearly the wrong solution.
Right.
But then you have, maybe then you have commutation and you don't want that, or like
So you're saying start with sum of sigma jz.
yeah. So it's maybe because it's commuting then, and that then you don't get any. So like because you
It will commute, yeah. So I think
because
it
you
will
have
commute with
2
it.
minus 1 and it
Yes,
is
and so you will never improve your cut value. Yeah. So
like that, linear and polar.
Will we go back to that one? This is again. The theorem, the discrete version of that.
No, it is coming in the same way.
And there is some sort of a like convergence kind of thing, or like how fast there is as t tends to infinity.
So those convergence rates depend on the discrete differences of
That's
the matrix
we
HC.
analyze problem by problem.
Yes, so the convergence, so at a very high level, the convergence constants are really difficult to compute. And they depend on some sort of what's known as discrete differences of the matrix HC. And even in the QAOA case, we don't know how to, like, the expressions are not going to be simple in terms of n or t, or in terms of n, yeah. We don't know how to write those expressions in a way that's meaningful in terms of convergence. And it's a big open problem as to how to do that, yeah. So let me
So evaluating the convergence rates itself is more.
to write the convergence rate in a way that's meaningful, right? Like in terms of just in terms of n is open, like purely in terms of n, yeah. Or maybe just in terms of, I don't know, the highest weight in the graph or the sum of weights in the graph or something like that. So let me now talk about warm starts, which is the idea of how to warm start or how to give QAOA a better start. And then I'll talk about custom mixers, which is, okay, even if you do a warm start, what's the guarantee that you're going to converge? Because now you're starting in a state that's different, right? So let's talk about the Goemans-Williamson algorithm. So even if no other details are known, we know that we obtain n vectors that are n-dimensional. And let's suppose that, and then these are real vectors. Let's suppose that these are represented by the circle here, right? And a cut, how is a cut obtained? You just choose a random hyperplane going through the origin. So something like this. So it goes through the origin. Everything on one side, I'll put on one side of the cut. Everything on the other side, I'll put on the other side of the cut. So let's not worry about how to obtain these vectors, but that's the process. Now, at a very superficial level, there is a similarity between this and quantum states, which are also unit vectors in a big sphere. Of course, this is n-dimensional and those are different dimensional. And so even before I go there, it's known to be a 0.878 approximation, and there is a family of graphs known where this 0.878 is typed for this algorithm. So here's the idea, right? A very perhaps a very simple thing to try, and why should it even work? I would not expect it to, but it does. So let's look at these vectors. These are n-dimensional vectors, and I showed you the block sphere, which represents one qubit, right? Which is like this 3-dimensional wall. So let me just round these vectors to 2 or 3 dimensions. Let's say 3 dimensions, and map it to the block sphere, and that's how I'll get my warm start. There is a very superficial similarity between block sphere and the picture I showed here. They are just vector in different dimensions, but somehow this technique of just rounding these vectors of Goemans-Williamson to the block sphere to get a warm start, it works. So this is the warm starting of QAOA. So we obtain Goemans-Williamson solution vectors. Pick a random k-dimensional subspace of Rn. So pick a random k-dimensional subspace, k is 2 or 3. Pick a unit vector uniformly at random, and pick a random unit vector in Rn uniformly at random, project it onto A, let's call that V prime, and I'll map it to the 0 bit on the block sphere, right? And for each vertex or for each vector Vj that corresponds to a vertex, first compute its projection on the 2 or 3 dimensional space, and then map it to the block sphere. So if your dimension is 2, map it to the xz plane on the block sphere. Otherwise, map it to the block sphere. So these details don't matter, but the idea is that you just take something that's an n-dimensional vector, round it to 2 or 3 dimensions, and just map it to the block sphere, which is like represents one quantum bit, right? So we'll call this QAOA1. And this is basically a schematic of what happens. So this is the Goemans-Williamson SDP solution. So these are the vectors we went through Vn. Goemans-Williamson showed that, well, if you round it to one-dimensional space, which is the hyperplane rounding I described, then you get a 0.878 approximation. This time what we are doing is we are first going to a k-dimensional space and maybe then going to the one-dimensional space. So that's all still classical. So the first lemma shows that basically these two processes are equivalent. So you take these n-dimensional vectors, you round it to say 10 dimensions and then to 3 dimensions and then to 1 dimension, you get the same distribution of cuts. Now, to introduce some quantum computing here, we just exit here, we don't go further. We do some sort of rotation, which is the randomly choosing a vector. We create an initial state of QAOA based on this and run QAOA, and then you get a cut. And this works better than standard QAOA in theory and at depth 0, meaning even before you have started the circuit, this has a non-trivial approximation more than what QAOA has. Right?
But that is because Goemans-Williamson.
That is because Goemans-Williamson, yes. Exactly, yeah. You could, of course, like take the actual cut from Goemans-Williamson and map it to the block sphere. But the non-trivial part of this is that doing that makes sure that your algorithm converges, like the QAOA then converges really, really slowly. It is somehow important to take Goemans-Williamson solution, map it to 2 or 3 dimensions, and do it.
So if you do it in map it to one dimension, then you only get so what do you get? You just get the same, they can only differ in phases. So,
You get a 0.878, a cut that's a 0.878.
But in terms of the bomb start for the algorithm, the states, so you just get like a phase factor in front of something. Or what
You'll get a classical bit string.
just one bit string.
Just one bit string.
Just one bit string. And yeah, so it's again the same problem because there's the point is that this the original matrix, the HC, the sigma z, it's a diagonal matrix in that basis. So this is already an eigenvector.
It is an eigenvector, yeah, and it gets stuck very quickly.
And therefore it just gets stuck.
It gets stuck, yeah. And then you can, as you said, you can show that it doesn't make progress. So it's important to have a 2 or 3 dimensional sort of rounding. That's the only non-trivial part here. So
this gives you a cut, but you also need a matrix. How do you get that?
yes, so that's the custom mixers part, which says that, all right, so with warm start, we start in a state that is different from the uniform superposition. And I'm omitting a lot of the details, but essentially you need a corresponding matrix which has this new state as unique highest eigenvector. And you can basically, if this initial state is separable, right, which we constructed just now, then there is a way to write this mixer. So you, for the jth bit, you will write it as something like this, based on the block sphere representation, and then you'll just add them up. So I'm omitting all of the details here, but essentially you can write an explicit form of this mixer term HP prime, which is why it's called custom mixer, but you can essentially construct that matrix. And it's not so straightforward to show that it converges, but the idea is that, all right, it has a unique highest eigenvalue, and at each time as you go from H prime B to HC, you maintain that there is always a unique highest eigenvector. That's non-trivial to show. I'm omitting the proof here. And we call this variant QAOA warmest. The previous one was QAOA warm. And the first theorem is that with custom mixers, you still converge. So even with warm starts, you cannot now converge, right? The second theorem is that, all right, even as you start with the Goemans-Williamson warm starts, you have this approximation, and because QAOA never decreases the approximation, so it's monotone in the approximation, the hope is that one is able to get over the limitations I mentioned for 3 regular graphs and so on. So our conjecture is that this sort of is strictly better than QAOA as the depth increases.
I don't know something that go out. What is so for the second theorem? I thought you already had 0.755.
No, so this is at depth 0, as in even before you have started the quantum circuit, you are already in a state where if you just do quantum sampling, then we'll get this approximation. So in standard QAOA, this number is 0.500. And so even as you're starting, this number is more than what you have there. Plus, there is a guaranteed convergence to the optimal as you increase the depth.
That is theorem one.
Yeah, that's theorem. That's the first theorem. Yeah. So, and empirically, this is what happened. So, in non-noisy regimes, so the green one is Goemans-Williamson. If you do the standard QAOA, that is the standard ideal, the orange one, then you do exceed Goemans-Williamson at depth 4. But if you do this warmest, then you not only, of course, you start at a much better number, and then you keep improving also. Of course, in noisy regimes, even standard QAOA quickly goes down in its approximation ratio. But in noisy regimes, this variant warmest seems to hold much better against noise, and hopefully, as our techniques to reduce this noise improve, these approximations are going to not go down and keep going up.
Sorry, what are these noises referring to?
Decoherence noise in the quantum system. Yeah. And so here's a
So you're saying the empirical performance suggests if there is no noise, then this would actually be doing better than Goemans-Williamson.
for a specific graph.
And what happens on?
Or for a specific graph.
Yeah, and this holds for like many graphs, but this is an example of.
These are the instances which are hard.
So, but there are also these code-based noise tests, which are harder for even like like hierarchies or things like that. So what happens for those? Or
I'm unaware. So did you say code based?
no, I think code and mission. So basically based on 5 construction like this. So I don't know what the carbon construction is, but there's this continuity to 5 which sort of I think says that you basically make up firstly a infinite graph, which is basically designed to make Goemans-Williamson correct in this like tight in the sense that you basically connect things at a certain angle, which is the same angle that 2 by 5, whatever that comes up. And then there are discretizations of that, which is paper of
So that sounds very similar to the constructions of Karloff.
Yeah, but those ones are shown to be like. So the thing I'm asking is like there are ways to improve Goemans-Williamson by adding more constraints, like so adding it to square constraints and like so basically what will correspond to let's say a hierarchy. And I think these are shown to have like up to a certain level of the hierarchy.
Right. So even if you add those constraints, you're not going to be able to improve the bounds, right? So those are, I believe, generalizations of Karloff's instances. I don't think we ran this experiment on those instances. Yeah, but that would be interesting too. Yeah. So very quickly, I'm actually out of time for the second half of my talk, but let me skip this and let me just describe the problem quickly instead of going into the nitty-gritty. So we have two types of quantum gates: so e to the minus I alpha sum cost Hamiltonian, right? So these gates must be compiled on quantum hardware, right? So you also need to produce these gates by combining them from small gates.
So in these empirical results, these are done on quantum circuit, like or like are they done on like say something like some IBM thing or?
So this is on the ideal ones are of course simulations, but the noisy ones are on IBM Quantinuum.
How many qubits?
So this is 20 qubits.
Oh, 20 qubits then. So the number of qubits is.
Yeah. The next Karloff instance is of size 120.
Mm-hmm.
So it's that's challenging. So the only options are 20 and 120. So let me just quickly describe the problem and maybe I'll end there and not go into the detailed constructions and so on. So you want to create this sort of Hamiltonian, and you'll be given like fundamental operations through which you can construct this sort of gate, right? Because this is not going to be directly available to you. You still need to construct this. And let's call these coefficients as forming a target graph. This is different from the max cut graph. This is a separate graph with edge weights or something, right? So on trapped ion hardware and for other hardware, there are similar sort of operations and so on. But the main idea is that, all right, you can have a bunch of smaller operations using which you can make this bigger one. And these operations on trapped ion hardware look like this. So you add a complete graph, which we call a pulse weight W, and you flip the edge weights of certain bits. And these are the two operations. So one is a global operation and the other is a local operation. Different hardware have different sort of operations, but the crux of the idea is the following. All right, so maybe you can combine these operations to get something like HC, that sort of target graph. But it is very crucial to do this in as number of steps as possible because of quantum noise and decoherence. The fewer number of operations you use, the fewer number of fundamental operations you use to do this, the better the noise is. And so this becomes its own optimization problem that has connections to other graph theoretic optimization problems. So this is the problem. So of course these are the two reasons why I want to do this. And as a quick example, if that's your target graph, so in the first iteration, what you do is you add a complete graph of weight minus half, and you flip the weights on vertex C. And in the second iteration, add another complete graph of weight half, and if you add these two, you basically get that. It's unclear if you can do this in a polynomial number of operations, as in you can combine these basic operations and get any target graph in a polynomial number of operations. We show that this can be done in a polynomial number of operations in a construction called union of stars, because it's a union of star graphs, that's why. And then the so the takeaway, even if this specific construction is only for specific hardware, is that having one global and one local operation, simple operations, allows you to construct arbitrary cost Hamiltonians that correspond to these graphs. And this is true for various different hardware. And in a non-trivial way. So this is not obvious how to do. I will have to skip this. Quickly say maybe that, all right, so in the first iteration of the algorithm, we show that all right, the number of operations is order n for unweighted graphs, order m for weighted graphs. In the second operation, we improve it and so on. And the ideas are very simple from classical computing. I'll skip all of this and just say that these methods do lead to quite a bit of noise reduction. So the yellow one is our method, and the blue one is what happens if you just apply like the classical, like the previous techniques or something. When you have some noise, on the left you have no noise. When you have some noise, then the yellow one starts to become competitive with the blue one. And when you have a lot of noise, then the yellow one is significantly more competitive than the blue one, and the purple one is on the gradient. So the higher on y-axis, the better it is. So under noisy regimes, the yellow and purple ones, that's our algorithm is competitive or beating the blue one, which is the previous one. So three quick takeaways. So hybrid quantum classical algorithms now perform pure classical or pure quantum algorithms. One starting QAOA with classical algorithm leads to improved performance, and convergence can still be guaranteed. And finally, classical techniques to speed up these quantum circuit compilations can help reduce overall noise in the quantum system. So there's a lot of opportunity for discrete optimization problems to be applied in quantum systems, even if just to reduce noise. Thank you so much for listening. It's based on these three papers. I'm very happy to take any questions. Thank you so much.
Have people studied like what happens if you start with the Goemans-Williamson solution on a Carlock instance and do local search around it?
Do local search around it.
Like try to change a few of the effects values.
So
like small
So I don't know if what happens empirically, but in
So, for
theory,
example, like was one like the solution is beyond the Goemans-Williamson, are they close to the Goemans-Williamson solution in sort of timing distance, or are they really different? Like,
so I think that I'll have to double check. So I'm not sure about this, but I think they are at each step of the algorithm, they don't change by that much. And I think even at depth 4 or 5, there are significant similarities to the Goemans-Williamson solution.
no, but what I was wondering is like this also says that in practical situations might be helpful to, like if you don't have a quantum computer to Goemans-Williamson, then you will local search.
Yeah, two things. So one, of course, in theory, this will not work.
In theory, yes, like, but
Yeah,
like,
yeah,
in this one instance, so like similarly, like empirically, are the, like, for example, for Karloff instances, is it true that local search can.
Probably because the classical heuristics beat everything. So if you just run classical heuristics, then they'll give you 0.9 in approximation for very large dot variability, and they are based. A lot of them are based on these local sets of algorithms.
Any other questions? So you're here till tomorrow morning?
Yes.
Yeah, so Jay is available in 8 to 8 tomorrow also, the first half. So can we?